Here in this example, we want to look at another very common and very powerful technique in circuit analysis. This is called nodal analysis. The nodal analysis based on Kirchhoff current rule. So we first identify node. In this circuit, we have node A, B, C, and D. We first have to mark a point where the potential is 0. It means we have to decide the reference potential. In this question, we say D is the reference potential. It means the potential here is 0. So this is 0 and this is 0. Next stage, we want to find a node and write down the KCL for this node. In this example, we're going to write the KCL at node B first. Next step, we have to assume the direction of current. Either they are flowing into the node or flowing out the node. So we have to make some assumption. But remember, even though our assumption is incorrect, after this calculation, you will just find the negative value. We can make an assumption of the direction of current based on our guess. Say, for example, here, I will say the current passing through R1 will flow into the B, and the current passing through R2 will also flow into B, and assume the current passing through R3 will flow out from the B. So I will put this I1, I2, and I3. So now let's write down the KCL at node B. KCL at B. Now the first current going in is I1 and also I2. But if you look at the circuit, I2 must equal to IS because we have a current source here, and the current source IS must equal to I2. So instead of putting I2, I can just put IS here and I3 flowing out from the loop B. So this is I3. Next, we want to express all current in terms of node voltage and resistance. This is the key step in the nodal analysis. Let's first analyze I1. Remember Ohm's law, V equal to IR. So I equal to V over R. So it means instead of putting I, we'll express I in terms of V over R. For I1, we first see which side of the potential is higher. This is A. So the potential at A is higher than the potential at B. So we'll say this is VA minus VB. So remember, the rule is from the high potential to the low potential. And then we have to find the difference. This is the potential difference over R1. Now, if you look at the circuit, VA must equal to 5 volt. So we can say 5 minus VB. At this stage, we don't know. We just say VB over R1 is 1K. I2 is IS and is equal to 2 milliamp. I3. Now, if you look at I3 flow from node B to the ground. So the potential at B must be higher than the potential at D. So the rule again is the voltage from high potential minus the voltage of the low potential. And the resistance is 1K. Now we can rewrite the KCL in terms of the voltage and the resistance. So I1 is 5 minus VB over 1K plus IS, we just say 2M. We keep the prefix, but we don't need to put the unit again. Equal to I3, we just say VB over 1K. So we have an equation which is have VB as its unknown. So we can solve this equation. Now this equation has 3 terms. And the denominator is 1K. So we can multiply both sides by 1K. So it means we multiply here by 1K. We multiply here by 1K. So this becomes 5 minus VB plus 1K multiplied 2M equal to VB. Again, K multiply M equal to 1. So we have 5 minus VB plus 2 equal to VB. So we have 2VB equal to 7. And VB equal to 3.5 volt. The voltage at node C can be calculated from the potential difference between B and C. Now let's just put A is 5 volt. B, we just found this is 3.5 volt. And we want to find the voltage at C. So we can say VC here. And we can apply Ohm's law. And Ohm's law say I2 equal to IS. And this is equal to the high minus the low. It means the current is from VC minus B 3.5. And the resistance here is 2K. Now remember, this is equal to the current I2 or IS. It means this is equal to 2M. So let's solve this equation. VC minus 3.5 over 2K equal to 2M. So now VC minus 3.5 equal to 2M multiply 2K. Again, M multiply K equal to 1. We have VC minus 3.5 equal to 4. So VC equal to 7.5 volt. Next, we want to find the current passing through R1. This is I1. I1 equal to the potential difference across R1, which is 5 minus 3.5 over the resistance, which is 1K. So we'll get 1.5 milliamp. Find the current passing through R3. I3 is equal to the potential at B, which is 3.5 over the resistance of R3, which is 1K, and we got 3.5 milliamp. Now we can verify the KCL now. The KCL say I1 plus IS, so this is equal to I1 1.5 milliamp plus IS, which is 2 milliamp, and equal to 3.5 milliamp, and this is exactly equal to I3. This circuit has one current source, which is 2 milliamp. Now node C is grounded, so the potential at node C is equal to 0. Next, we have to assume how the current flows. Now we can say IS goes straight up to the A, and there's a different option about I1 and I3. Let's assume current I1 leaves the node A, and the current I3 leaves the node 8 as well. So the KCL at A will be IS equal to I1 plus I3. This is equation 1. Note B, there's an I3 going in, and if we say I2, which passing through R2, will go out from the node B. So this is I2. So KCL at B is I3 equal to I2. So this is equation 2. Next, we want to express all current in terms of node voltage and the resistance. Remember, V equal to IR and I equal to V over R. So we want to find the potential difference across the resistor over the resistance. For I1, the I1 will flow through R1. So this must be high, this must be low. And this point here, this is the voltage, same as VA. And after the current passing through R1, its voltage is 0. So we can say I1 is equal to VA or V1, because now we can mark the voltage at A as V1 and the voltage at B as V2. So this is V1 minus 0 over 1K, or just put V1 over 1K. I3, V1 is high, V2 is low. So because I3 is from A to B, so I3 from A to B, it means V1 high minus low. So the order is very important. So this is 1K. I2 is from B, it means V2 to 0. So I2 is V2 minus 0 over 2K, or just say V2 over 2K. So from equation 1, IS is 2 milliampere, 2M. I1, which is V1 over 1K. I3, this is plus V1 minus V2 over 1K. This is equation 3. From 2, I3 equal to I2. So V1 minus V2 over 1K equal to V2 over 2K. So this is 4. Now to find V1 and V2, we notice this term, the denominator is 1K, 1K. And for equation 4, the denominator is 1K, 2K. So we can first tidy up this one. So we say 3 multiply 1K. So this is 1K 2M equal to V1 plus V1 minus V2. So we have 2V1 minus V2 equal to 2. So this is equation 5. Next, we want to simplify equation 4. We multiply equation 4 by 2K this time. So 4 multiply 2K. So you got 2 V1 minus V2. And this is V2. And we have 2V1. And we have minus 3V2 equal to 0. So this is 6. So we can say 5 minus 6 for V2, minus 1, minus 3, and this is V2, 2 minus 0. So this is equal to 2 V2 equal to 2. So V2 equal to 1 volt. We substitute V2 equal to 1 volt into 5. So 2V1 minus 1 equal to 2. 2V1 equal to 3 and V1 equal to 1.5 volt. So just put it here. V2 equal to 1 volt. So this is the solution. So we found that V1, it means the potential at A, is equal to 1.5 volt. And the potential at B, which is V2, is equal to 1 volt. Now the current I1 is equal to V1 over K, and V1 is 1.5 volt over K, so it means 1.5 milliampere. For I3, it is equal to V1 minus V2 over 1K. V1 is 1.5 minus V2, 1 over 1K. So the answer is 0.5 milliampere. I2 equal to V2 over 2K. V2 is equal to 1 volt and over 2K, and you get 0.5 MA. So remember, I3 must equal to I2. So this is agree. Next, we are going to check if the KCL at node A is correct. So at node A, the KCL say IS, which is equal to 2MA. And also let's check I1 plus I3. I1 is equal to 1.5 milliamp. I3 equal to 0.5 milliamp. So the sum is 2 milliamp. So KCL at node A, it is correct. Let's first find the reference potential. We make node C the ground. So this becomes 0. Now we have to assume how the current flow in this circuit. Now remember, this is an assumption. If our assumption is not correct, the calculation will reflect this one and will give a negative sign. So the current passing through R1, we call the I1. We assume the I1 flow into node A. And then we have an IS, and this is passing through from A to B. This is the current source. We assume I3, which is passing through R3, flowing out from node A. So at node B, we assume this is, of course, I3. And then we assume IS and I3 combine and become I2, and which will pass through R2. So let's write down the KCL at node A and node B. KCL at node A, we can say I1 equal to I3 plus IS. And this is equation 1. KCL at B, this is IS plus I3 equal to I2. This is equation 2. Now, this is the key step in any nodal analysis, which is express the current I in terms of V over R. The voltage at A, we just call VA. the voltage at B, we call the VB. So for I1, we look at R1, and this part must be high, and VA must be low, because current always flow from the high to low. This potential is actually equal to 0. So it means we have to put I1 equal to high, which is 0 volt, minus VA. Remember, potential can be negative. So we just know A, the potential at A must less than the potential at C. So 0 minus VA over 1K. Or we just put minus VA over 1K. I3 again, this is VA and this is VB. So the potential difference is from high to low. It means VA minus VB over 2K. How about I2? I2 here is VB from high to low, which is 0. So I2 equal to VB minus 0, just VB, over 2K. Once we write down the current in terms of V over R, now we put this back to the KCL equation. So from 1, it will become I1 minus VA over 1K equal to I3 VA minus VB over 2K plus IS. IS is 1M. 3 from 2, it become IS. IS is 1M plus I3. This is VA minus VB over 2K, and this is equal to I2. I2 is VB over 2K. This is equation 4. Now again, we look at the denominator, and equation 3, the denominator is 2K and this is 1K. So to simplify the equation, we will say 3 multiply 2K. So we have minus 2 VA equal to VA minus VB. Now remember, 1M also need to multiply 2K. 1M multiply 2K is 2. So we have plus 2 here. So we can tidy up this one, become 3VA minus VB equal to minus 2. This is equation 5. For equation 4, we can say 4 times 2K, the same. And again, when 1M multiply 2K, it becomes 2 plus VA minus VB equal to VB. So we can say VA minus 2VB equal to minus 2. This is equal to 6. Now we can first eliminate VB. VB here, and the coefficient of VB in equation 5 is minus 1. And the coefficient in equation 6 is minus 2. So what we can do is we have to use subtraction this time. 5, but we have to multiply 2 first. And then minus 6. So the coefficient of VB will become 0. So how about VA? So 3 times 2 minus 6 is 1. And this is VA. Same argument. Equation 5 times 2 minus equation 6. So this is 5VA, and this is minus 4, and this is plus 4. So this is minus 2. And VA equal to minus 2 over 5, or equal to minus 0.4 volt. Now we substitute VA equal to minus 0.4 volt into equation 5. So we have 3 multiply minus 0.4 minus VB equal to minus 2. So VB equal to minus 1.2 plus 2. So this is equal to 0.8 volt. So we know the potential at A is minus 0.4 volt, and the potential at B is positive 0.8 volt. Next, we want to find the current I1, I3, and I2 and check if the KCL correct or not. So I1 equal to minus VA over 1K. So minus VA is equal to minus 0.4 over 1K. So I1 is equal to 0.4 milliamp. And because this is positive, so it is flowing from C to A, and it is correct. And this is consistent with the direction we assume. I3 is equal to VA. This is minus 0.4 minus VB. This is 0.8 divided by 2K. So you can say this is minus 1.2 over 2K. It means minus 0.6 milliamp. So the direction of I3 is actually reverse. It means in reality, I3 flow this direction, because we assume I3 flows from A to B, but we get a negative value. So it means it actually flows from B to A. So this is 0.6 milliamp if it's from B to A. I2 is equal to VB over 2K. VB is equal to 0.8 over 2K. It means 0.4 milliamp. So let's check the KCL. KCL at A. This is I1 equal to 0.4 milliamp. I3 plus IS. So I3, we just put the number here because this is minus 0.6 M. A plus IS is 1 milliamp. So of course this equal to 0.4 milliamp. So both sides, they are equal. The KCL at B, the left hand side is IS plus I3. So IS is 1 milliamp and I3 is minus 0.6 milliamp. So this is 0.4 milliamp. And I2, we found out which is equal to 0.4 milliamp. So again, the left hand side is equal to the right hand side. It means KCL at B is also correct.